Welcome to this presentation on linked list in C++. In this presentation we're going to actually look at some of the details of implementing a linked list in C++. As you recall from other presentation, we saw that a linked list was a collection of nodes where each node had one or more pieces of data and a pointer to another node that we could hook up, link up these different nodes, much like you would link up cars in a toy train set. We'll look at some of the details on how we can provide for certain operations that we might want to. So we'd want to be able to insert an item, remove an item, display the list of items, maybe count the number of items in the list. So let's see how we might do that. This is an old project that we saw in a previous presentation, and I'm just going to reuse the project by excluding this particular code and then adding a new item. Linklist.cpp. And I'm going to put everything in a single file to make it easier. I know the assignments ask you to have different header and CPP files, but for the purpose of this presentation I'm going to keep everything in the same. I'm going to keep everything in the same source file. Here's a we have a standard include for IOStream, so we can use cout, and we have the node class that we saw before. So it has a data, which is just an integer, but it could be anything. It could be a linked list of names or whatever. And we have a pointer to the next node. And notice my naming convention here is to put p in front of variable names that are pointers. It's just a convention that I use. Different programmers have different programming styles or conventions that they use. Here is the constructor for node, and the way the parameters are set up, the default parameter values here are set up, this particular constructor is set up as a default constructor and a parameterized constructor. So if you create a node without any parameters, it will default the data value to 0 and it will default the next pointer to null. And again, another convention that I like to use is to use the same names in the parameter list as the data members, but prefix them with an underscore, and so that we can keep them separate. It's just a convention that I like to use. So now we're ready to define a linked list. And I'll just make everything public for now. We can maybe change that later, and what we need in a linked list is to be able to store a pointer to the first item in the list. So it's going to be a node pointer, and then we might want a constructor, a default constructor for the linked list. And this indicates that the list is empty. At some point we're going to have a main function. We're going to declare an instance of a linked list, and we're going to do some things with it. In particular, we'd like to be able to insert some values or add some values. Error messages because we haven't written that code to do an insert. Let's talk about how we might insert values into a linked list. For the insertion, we start off with an empty list, and if the list is empty, then we just want the first thing in the list to point to this new item that was added. Say an 8 was added. And maybe we should rename this insert front because we'll be inserting an item to the front of the list every time. Here we insert a 4 into the list, and the way we do that is that the new node that we're creating that contains the 4, its next is going to be the same as what p first used to be, pointing to the node that has the 8 in it, and then p first is going to point to the new node that was created. So let's see how we might write that. We're going to create a new node. Dynamically allocated and constructed with the value and what should this node point to next. Well, in this case here, when we inserted the 8, that node should point to a null next because there's nothing else in the list. So you can see that the new node should point to, its next pointer should be equal to what p first used to be. And over here we have the same thing. The new node that we're adding, which is the node with the value 4, should point to what p first used to point to, the node that has the 8 in it. So before we change p first, we should set its pointer value, assign its pointer value to the new node's next pointer. And we do that by passing in p first to the constructor. So that creates a new node that in this first case, when we're inserting into an empty list, the next pointer will be null because p first was null. Or if the list is not empty, it creates a new node where p next is pointing to what p first used to point to, which is this node with the 8 in it. Once we've done that, then all we have to do is set p first equal to the new node. So now instead of p first pointing to the node with the 8 in it, it's going to point to the new node we created that has the 4 in it. So these diagrams, I think, are very useful in figuring out how to do these insertions and removals. And I find it extremely useful. The only way we can know if this works, I guess, is if we write some kind of code to print out the list or display the list. So let's do that. And in order to do that, we need the concept of traversing the list. And here's how this is done. Here we have a linked list that has 3 items in it. What we do is create a temporary pointer. Sometimes I like to call it a walker because it's going to walk along the list. And it's going to point to what p first points to. And then the next iteration, it's going to point to what p walker next points to. And then we're going to update it to p walker next. And at each iteration, we'll just print out the value of p walker data. And we'll keep doing that until this p walker becomes null. So you can do this with a for loop just like this. So you can do this with a for loop that looks just like that. So you can, instead of a, this may be a little bit different for loop, instead of a for loop that counts up integers, this is a for loop that steps across pointers to, in this case, pointers to nodes in a linked list. So pwalker is going to point to the same thing that first is pointing to, and then as long as it's not null, which means the list wasn't empty, we'll do something, and when we do the update for the loop, we'll set pwalker to pwalker next, which means it'll just move down to the next one, do something with it, move down to the next one, do something with it, which move down to the next one, and that will set pwalker to null, and then this test will fail and we'll break out of the loop. So in this particular case for display, we will just print out pwalker data, and when the loop is done, print out a return or something. And this traversal can be used in several different places. It can be used to print out the contents of the list. It can be used to count the number of items in the list. It can be used to sum up all the values, add up all the values in the list. So this is a common step for doing traversal. Of course, you don't have to use a for loop. You could do the same thing with a while loop. There's different ways of accomplishing the same thing. So we've got our insert front is what we're calling it, because every time we insert, the value is going to be added to the front of the list rather than at the end of the list. And we'll display the values in the list. So if this builds and runs okay, so I guess we'll get a warning here about main should be of type integer. That's no big deal. All right. So if we run this, then we see that we're getting the values 8642. So notice that the values are in the reverse order because we're always adding them to the front of the list. So the last thing added to the list is going to be the first thing in the list, because we're always adding to the front of the list in this particular case. We could add to the back of the list, but we'd have to write a slightly different function, insert back, and I think I'll leave that for you as an exercise to figure out how to do that. Something else we might want to do is, we haven't addressed the memory leak or the dynamic memory allocation. What happens when we're finished with the list? We should free up the nodes. And for that, what we may want to do is to remove a node from the front of the list. And if we can remove a node from the front of the list, then we can just do that over and over and over again until the list is empty. So let's add a remove function. And to remove a value from the front of the list, what we'll do is have a temporary pointer to the front of the list. And as long as that temporary pointer is not null, we will set p first equal to that temporary pointer next. So now p first will point to this guy, and then we'll take that temporary pointer and delete it or release the memory for it. And it might be nice to return the value that's removed. So I'm going to create a temporary node pointer called p2delete. This is the node that I want to delete, and I'm going to set it equal to p first. And as long as that node to delete is not null, which means that the node's not the list is not empty, then I'm going to set the return value equal to the node to delete data, and then I'm going to set p first equal to the node to delete p next. So this p to delete is going to point to the first node. I store its data in a temporary variable to return it, and I set p first equal to p to delete next. So now p first is skipping the first one and going down here, and once we've done that, then we can delete or free up this node to delete. What if the list is empty? If the list is empty, this if test will fail, and we get down here to the else. What do we want to do? Depends on the application. Maybe you want to print out an error message. Maybe we'll just set the return value to something negative or 0 or something like that. Depends on the application what you would want to do if you try to remove a value from an empty list. In some cases you may want to throw a C++ exception. Depends on the application. So then the last thing, well, not the last thing, but the next step is maybe to get the size of the list or the length of the list. How many items are in the list? And to do that, we're going to use this loop here. And inside the loop, all we're going to do is count up the number of items in the list. So every time Walker is not null, it must be pointing to a valid node, so we just increment count. Which then allows us to clear the list by saying while the list size is greater than 0, remove from the front. So we're just going to remove items one at a time from the front of the list as long as the size isn't not 0. The size is greater than 0. And then this allows us to create a destructor that just clears the list. So when we're finished with the entire linked list, we just clear out everything, free up all the memory. So now to test this, we can remove a value from the front of the list, store it in a thing called result, and then print out the result was moved from the list, and then display the list, and then say how many things are in the list. Maybe before and after we remove something. So if we run this, initially we get that there are 4 items in the list, 8, 6, and 2, and the value 8 was removed, it was in front, and now there's 3 items in the list, 6, 4, and 2. So that's the beginning of linked list code. There's at least one other function that we want to look at, and that is being able to remove a particular value from the list. So what if we wanted to remove a particular value from the list? Say we've got a list that has 4, 8, and 3 in it, and we want to remove the 8. Basically what we need to do is keep as we walk through the list, we want to keep a trailing pointer. I'll call it P left. And when we find the value that we want to delete or remove from the list, we take that trailing pointer, P left, and make its next skip over it to the next one. And then we can free up the memory for this pointer to delete. One particular issue that we have is that if the first pointer is null, which means it's an empty list, then we don't have a P left or a P to delete. So that it makes us have to write some special case code. So one strategy for this is to modify our linked list so that instead of the first data member of the linked list, instead of it being a pointer to a node, we actually make it a node or a pointer to a special dummy node that is the front of the list. And so in that way we can, even if the list is empty, we can have left point to the dummy node, which marks the beginning of the list. Its value doesn't matter. And the delete then would be null because it would be pointing to the next node. In the case of an empty list, the next node would be null. So instead of having the front of the list be a node pointer, what we can do is change this so that the front of the list is an actual dummy node. And the value that we put in that dummy node is never used. We're just using it as a special starting point to make certain operations like removing at a particular value maybe a little bit easier. So then we have to change some of this where we say front.data, we don't care what it is, and front.pnext is null. And when we do the insertion, this is going to be front.pnext for the new node. And front.pnext is going to be equal to that new node. So we just have to modify the code here in order to remove from the front. I'm going to set the node to delete to be pfrontNext. And pfrontNext will skip over the node to delete and point to the node to delete next pointer. And when we're doing our walking, our traversal, we have to initialize pwalker to pfrontNext. And I think that's all the changes that we need. And you see the output, the code does the same thing. So all we've changed is that instead of the front of the list being a pointer to some node, whether it's either null for empty or actually pointing to a real node, we've changed it so that now the front of the list, or the first thing in the list, is a dummy node that has both data and next. We won't use the data part, but we'll use the next as a pointer to the first thing in the list. And this makes certain operations easier, specifically this removing a value here. We can have the left pointer start out pointing to the address of the front, and then the P to delete to be the first thing in the list. And as long as P to delete is not null, we check to see if that's the value we want to remove. If it is, then we'll break out of the loop and we're ready to skip over that node that we want to delete and then free it up. If it's not the value that we want to remove, then we just update P left to move down one and update P to delete to move down one and check and see again. If P to delete goes all the way to the end of the list, it'll become null, and that means we did not find the value that we wanted to delete, so we won't remove it from the list. We won't do anything. So let's see what that might look like in the code. We want to remove a value, not remove from a particular location, but remove a particular value. And we're going to do something very similar to this loop. But instead of Walker, we'll call this P to delete. And we will set a left pointer. So we need not only the node that we want to delete, but we need the node to the left of what we want to delete so that we can skip over, update its next pointer and skip over the node that we want to delete. So in our diagram here, we need this left pointer so that if we want to delete the 8, we can make the node on the left point to the one that we're skipping over, the one that we're removing. Sorry, point to the next one after the one that we're removing. So that's why we need this left pointer here. And that's going to be equal to, when we start this loop, that's going to be equal to the address of the front of the list. So keep in mind now that the front of the list is no longer a pointer, but an actual node that has a dummy value. And so to get a pointer to this actual node, we have to take the address of it. So in the loop, we want to see if we found our value. So if P to delete data equals the value that we're looking for, then we just want to break out of the loop. So the purpose of the loop is to step through the linked list and try to find the value that we're looking for to delete. We need an additional update step. So in addition to having P to delete move down the list, we also need to make sure P left moves down the list. So we need an additional update step where P left equals P to delete, or P left equals P left next. Either one of those will work. Okay. They should be the same value. It should always be the case that P left next is this pointing to the same thing that P to delete is pointing to, so they'll have the same address. Okay, when we finish the loop, we want to know if we found the value that we want to remove. And we will know that is if P to delete if that's not null. So if P to delete is null, then what that means is that we got to the end of the list. If it's not null, that means that we broke out of the loop because we found a matching value. So that'll be the value that we want to delete. And I've got an issue here with a variable access where, because I defined the node pointer p to delete in the for loop, it's actually limited in scope to just the for loop. So I need to modify this. So maybe this would be a good place to use a while loop instead of a for loop. So I need to pull this declaration outside of the loop, and maybe I'll change this to a while loop, and that means I'll move this update here. Maybe that makes more sense. So we set p left to the address of the front of the list. We set p to delete to the first real node in the list. As long as p to delete is not null, we do a search. If we find it, we break out of this loop. If we don't find it, we update p left and p to delete, walking down the list. After the loop is done, if we found a node to delete, our steps are to set p left next equal to p delete next. So now this will skip over the one we want to delete and go to the next one. So that was p left next equals p to delete next. And we want to release the memory of the item that we're removing, so we want to delete the node that we want to release the memory for the node we're deleting. So that removes a specific value. So now we can ask the user to enter in a value the user to enter in a value, read it in from the keyboard, say we're removing that value from the list, actually do it, print out the list, and then print out the new size of the list. And let's put a few more values in there. Run it, so we initially have 8, 6, 4, 7, 12, 1. So we have 6 items in the list. We remove the first item, which was the last one added, which is the 8. So that gets removed, and now there's 5 items in the list. And now it's asking us, what would we like to remove? And when we do testing with data structures and a lot of code, a lot of algorithms, you want to test the endpoints as well as test some things in the middle. So we want to test removing the value at the beginning of the list, removing the value at the end of the list, as well as some in the middle. So can we remove the 6? And it looks like it got removed okay. And then we'll run it again, and we'll test the other endpoint. Can we remove the 1 that's at the end of the list? And that looks like that worked okay. And then maybe try to remove something in the middle of the list as well, maybe the 12. And that seemed like that worked okay. So this is the beginning of a linked list class, and you can think of easy to come up with different features that you may want to add to this. One is maybe you want to insert at the back of the list or remove from the back of the list. You might want to insert items in a particular order, like ascending or descending order. You may want the ability to sort the list. You may want to be able to sum up all the values in the list, compute an average. So there's different features that you might want in this linked list depending on the application, how it's going to be used. can also take this, so here's a list of some of the possible functions that you may want to have. You can also take this one step forward, where right now we have what's referred to as a singly linked list, where each node points to the next node in the list. So you can only traverse the list in one direction easily. In data structures, we can create different data structures in any way we want, and a modification to the singly linked list is what we refer to as a doubly linked list. And in this particular case, a doubly linked list would have two pointers, one pointing to the next thing in the list, and then another one pointing to the previous thing in the list. And so the node may look something like this, where we've got a pointer to the next thing in the list and a pointer to the previous thing in the list. So each node would have two of these pointers, one pointing to the right and then another one up here pointing up or to the left to the next thing. And that's referred to as a doubly linked list. So I hope this presentation on linked list was helpful. Please feel free to contact me if you have any questions.